Okay. Good afternoon. Today we'll just continue on the 4 concepts that we were studying. Hopefully I get to finish this and move on to synchronization lectures. Okay, so in the previous lecture, we talked about the interrupt vector table and the general procedure to handle interrupts and exceptions. Now, there's a specific thing that we have to consider when we're looking at system calls. Usually, there is only a single entry in the interrupt vector table for system calls. x86 has a single entry, and as far as I know, ARM also has a single entry. Now, when you enter the system call handler, you have to decide what to do based on the inputs that is provided to you by the user, because you have different system calls, right? You have open, for example, you have close, you have read, you have write, you have open socket, you have listening from a socket, you have sending packets system calls. So all of these system calls, they have the same entry point, which is the system call handler, and there you have to then decide what to do. So the first thing is you probably want inside your system call handler to have a well-defined system call entry points. So you want to say, okay, based on the system call number, for example, that is provided to me, I decide to go to this system call or that system call. So based on the system call number, you decide which function to call, to read from a file, to write to a file, to listen to a socket, and so on and so forth. So that's the first thing you have to do. The second thing you need to do is you have to locate the inputs that are provided to you by the user. For example, if you want to open a file, you need to know the name of the file or address of the file. If you want to write to a file, you want to know what you're writing to that file. So there's a data that you want to write. So these are the inputs that are provided to you by the user. Now, where are they? They are on the user stack, obviously, right? Because user doesn't have any access to kernel stack. So it's kind of, for the user, it's kind of like a call to a function. You put all the arguments, that function, on your stack. So now we're in kernel mode. We have access to the user stack. We can go and fetch whatever input user has given us. So some of it could actually be in registers, right? So it's either in registers, if there are, like, you know, let's say if it is a single number, or they might be stored on the stack. I got a question I will answer later. Now, at some point, right, you have to check the integrity of the data that is provided to you by the user. You should not trust the user that the data that is provided to you is correct. The user could provide, for instance, a file that does not exist, or a file that the user doesn't have permission to, or maybe it wants to inject code to kernel code. So there should be some checking of this data that is provided to us by the user. Now, when should we check? The answer to that is there is this concept of copy before check. So the first thing we need to do is to copy that data to kernel memory, and then we can do the check. Now, you might say, why don't we check when the data is in user memory? And once we're sure that the data is good, then we can copy it to kernel memory. And the answer to that is, don't forget that you might be actually having a for example, multi-core setting where, pardon me, So it could well be that there are multiple threads running in the context of this process, and one of them has called system call. Now, the other threads still have access to the stack of the thread that has called system call. Now, if you check the data, and let's say it's all good, before you copy it to the kernel, one of those threads could go and alter the data. So you check right before you copy it to your kernel memory, one of the threads mess it up for you. So now you cannot use that data. So to avoid this, we just copy it first, and then we check it. So first we copy it, then we validate the arguments that are given, and then we call the system call, we handle the system call, and once the result is back, we copy it back to the user memory. So few numbers here. This is an experiment here on the height of each bar indicates how long it takes for that particular operation. So let me zoom in a little bit. So here, for example, you have different machines, like you have Intel, you have AMD machines, different cores. The color of each bar indicates a different operation that is being done. In particular, we're interested in two of these bars. I'm not going to talk about the red bar. So we focus on these two. So the first one is a normal system, a normal function call, a normal C function call. These are the blue bars, and the green bars are system calls. And the height of the bar shows you how long it takes. And as you can see, a normal function call takes around 7 nanoseconds on Intel, on this particular Intel core. And a normal system call takes about 220. And this is particularly associated, the cost is associated with the mode switch and all the tests that you have to do, and then going back to the user. So the going from user to kernel mode, processing the system call, and then going back to the user mode. And all of that is basically a lot of overhead. So just to note that system calls are very expensive, and we want to avoid them as much as possible. Okay, let me answer questions before I move on. So what is quiz 2 on? Only to the end of 0.2 concept or further? I have answered that question in my email. So please look at the email I sent. You get the answer. Okay, so when a user makes as a system call and the kernel needs to read from the user stack, what happens if the user stack is malformatted? What does the Okay, so I don't exactly know what you mean by malformatted, but at the end of the day, user stack is somewhere in memory, and you read some number of bytes from there, you copy it to your kernel memory, and then you start validating it. If the bytes that you're reading are garbage, then you detect anomaly and you abort. If the bytes that you've read make sense and there is nothing wrong with them, then you process the system call. Otherwise, you abort the mission, you return error or whatever the system call does. The other question I get: how does the kernel check for malicious code? I don't exactly know what you mean by malicious code, because so far we're just talking about data, right? And when data is passed to us, we just make sure that the data that is passed to us makes sense. Now, generally speaking, usually operating systems provide some assistance in isolating processes, so that if one process is malicious, the code is malicious, it cannot mess other processes. But as we will see, there are some, some ways to get away with it, using the shortcomings of the software, using the shortcomings of hardware, but more specifically in the case that we will, if we have time, we will study, it's the shortcoming of the hardware. So operating system is doing its job, but because of some side channels in hardware, a malicious code can indeed bypass operating system's isolation mechanisms and access other processes' memory. So if we get a chance, we'll talk about that. Are there system calls that involve passing a pointer to the user's heap to the kernel? Probably yes. Like if you're, for instance, writing some data to a file and that data resides in your heap, then yes. So you get a pointer. So you probably want to go and read the entire file. We'll see about that. There's an example at the end of this lecture, probably answers that question. Yes. Okay. So this is a slide. Before I finish this lecture, I want to talk also about monolithic versus microkernel operating systems. So whatever I talked so far, we have been focusing mostly on this monolithic kernel model, where most of the kernel functionality, basically whatever the operating system, I take a step back. Most of the operating system functionality runs at kernel mode. So the port that is important is this kernel mode versus user mode. So in monolithic kernel model, everything that the operating system has to do, it will do it in kernel mode, in the supervisor mode. The danger of this is that you will have a lot of code that is running in kernel mode, and kernel mode is basically whatever you want to do it, right? You can do whatever you want. And if you have a bug, then this could mess up your entire system. And if you have more code running in kernel mode, then there's a higher chance that a bug is found, and the bug could mess up your system. The idea of microkernels was that let's minimize what can run in kernel mode, and we probably want to just run the bare minimum in kernel mode. Other functionalities of operating system, things that operating systems should do, we'll run them in user mode. Now, this idea is very appealing if you care about security and reliability of your code, because the bugs, if there are any, will be in user mode and they cannot jeopardize your system. And if the code in kernel that runs in kernel is a small, we can verify it, maybe formally verify it, and the chances of bugs messing up our systems is really low. However, with this high reliability comes performance cost. The cost is, well, now that you want to run these servers, these services that operating system provides in user mode, you will end up having to do a lot of process communication, because your application, your processes are running here, and then you have a bunch of other processes running here. And if your application wants to communicate with each one of those processes, there has to be a lot of context switching and inter-process communication. So your application should just call into the kernel, and then your kernel has to go to this service that you want. And then this service, once it's done, it goes back to the operating system. And then the operating system goes back to the application. And probably this continues, right? You keep coming to the operating system, go back, and then go up, and so on and so forth. So this is basically a lot of inter-process communication, a lot of mode switches, and that's expensive, right? So that's the cost that you're incurring because of this. So this microkernel model did not go and did not become mainstream. Today's operating systems are kind of hybrid. So, you know, we don't do everything in kernel mode. For example, you have all these system libraries that you have, maybe your file system, maybe, you know, parts of it. No, not file system, sorry. This is the file server. But a bunch of servers run in user mode, but you also have enough in kernel mode that you don't incur the cost of going back and forth between kernel and user processes and a lot of user inter-process communication. So that's that. Yeah, so this shows you that, you know, many of today's operating systems like, you know, Linux, you know, OS X, they kind of adopted this idea of hybrid kernels. Okay. So finally, we've talked about going from kernel to user. Now let's talk about user to kernel. Like, there are a bunch of things that could trigger this kernel to user. For example, if you want to go back from an interrupt, or if you want to go back from an exception, or if you have created a new process and you want to now start running it. These are all going from kernel to user mode. The other one that we talked about is signals, right? When you get a signal, you initially, the signal is handled in operating system, and then operating system looks and sees if the, for example, if the process has a signal handler. And if it does, then it switches back to the signal handler and runs that. And that's a kernel to user mode switch. So this is kind of like a figure talking about all of that. You know, when you start executing your process or your thread, you go from kernel mode to user mode. And when you're done, you go from user mode to kernel mode. But during the execution of your thread or your process, you keep calling to kernel for system calls, for example, or for interrupts. If an interrupt happens, you go from user mode to kernel mode. And maybe you have to go now talk to the hardware directly with the help of the driver, and then eventually come back from it, and so on and so forth. Or an exception happens, and which we talked about. Now, putting all of this together, using this two-mode operation, operating system provides this interface, which we call the system call interface, to the user programs to use the hardware. Now, one essential part of this system, ecosystem of system calls, is when you actually want to go and talk to the hardware. And that usually happens using the device driver. So device driver is a code. It's specific to a specific type of hardware, and it communicates with the hardware and you know, knows how to talk to the hardware. Usually, device drivers are partitioned into two pieces: the top half and the bottom half. The top half gets involved initially when you want to send commands to your hardware. So, for example, if you want to tell your SSD to write some data to the storage, so you communicate with the SSD and you say, here is the data, go and write this data in memory to SSD. So that's the first part, that you command the device to do something for you. Now the device goes and does that, and once it's done, it raises an interrupt that I'm done with what you told me. At this point, the bottom half of the device driver wakes up upon receiving the interrupts, the kernel calls the bottom half of the device driver, and the bottom half basically does the housekeeping, says that okay, now that it's the service has been delivered, what should I do? Like, for example, copy the data from the device. For example, if let's say you receive the packet and the packet is now in your NIC hardware, now your device driver maybe wants to copy it to kernel memory or something like that. So after you receive an interrupt that I have a packet, then the device driver does what it has to do. So let's look at it in this diagram. So it all starts with a user asking for a service through the system called interface. Now the operating system looks at what it has. It might be that, for example, you're reading from a file and this file has been read before. So the operating system can locate the file, the data that you're looking for in memory. So we don't need to go to SSD. So if we have it, then we just return to user here. So if we have, then we can just go back to the user. If we don't, then the hardware, the operating system sets up the request and calls to the top half of the device driver. Now, the top half of the device driver sets up the kernel, sets up the device, so sends commands to the device that this is what I want you to do. So these are the control commands that are sent to the device. Now, at this point, probably the operating system have context switched this process, and we're running some other process while this request is being processed. So the device will take care of what it has to do. Once it's done, it raises an interrupt. At this point, the bottom half of the device driver gets involved, does whatever it has to do, passes it to top half passes it to the kernel, and kernel passes it to the user. Now, there are two types of data transfer between memory and I/O devices. The first method is called programmed I/O. In this method, every byte that we're sending to the device involves CPU time, involves the CPU to do this. So the same way that we do load and store, for example, to write to memory, we might have in-out or load stores to the device. We'll talk about these two in more details when we talk about I/O, but generally speaking, for each byte, we execute an instruction on CPU, and that instruction moves data to the device. If we want to read from a device, we do in or load. If we want to write to the device, we do out or store. But then these operations work byte by byte. Now, this is simple, right? Simple model, easy to program. The cost is CPU cycles. So let's say if you want to write or read 1 gigabyte, then for each byte of that, the CPU has to do it. And while the CPU is doing that, it can't do anything else. So we're just wasting CPU cycles for data transfer. To deal with this and make it easier and have better performance, direct memory access, or DMA, is proposed and used in our systems. What does DMA do? DMA, basically, we delegate the job of transferring data to a microcontroller. So instead of CPU doing it, a DMA engine does it. Now, we run the device driver. Device driver sets up the DMA engine, and then the DMA engine transfers all the bytes. And while DMA engine is doing it, CPU can do something else. CPU can move on to running another process or another thread, right? And once it's done, once the data is transferred, the DMA engine raises an interrupt, and CPU now wakes up and says, okay, it's done. What do you want to do next? Now, a DMA transfer usually has a couple of steps. Now, I have to say that the figure that you're looking at is kind of like old style DMA, where so in old systems you had on your processor chip, you had a DMA engine or two or whatever number of DMA engines, and these DMA engines, so in this case, this DMA bus interrupt controller was in charge of doing all DMAs. So no matter how many devices you connect to this bus, they would be all using the same DMA engine. Nowadays, if you buy an SSD, or if you have a modern NIC or a GPU or whatever you have, they have their own DMA engine. So they don't share with each other. So each one of them comes with not only one, sometimes bunch of DMA engines, right? So each device gets its own DMA engine. So I'm not going to talk about that one, but the steps are fairly similar, right? In this figure, you have the case where there is a single DMA engine that everybody uses. So let's look at that. What happens is that initially you're running your device driver on the CPU. Device driver talks to the disk and says, I want you to read this much data from memory, or I want you to write this much data from memory. So whatever that is. So you basically set up a buffer with a starting address and a size. You say, this is where I want you to put the data, or this is where I want you to read the data from. So this is the address, and this is how much data you have to transfer. And now you're on yourself. So then the device driver, the device now communicates with the DMA engine and says, okay, I have a DMA request, let's transfer data. Now the DMA engine starts the DMA, so the data transfer happens. Now from memory to the device or from the device to memory, it doesn't matter. So we transfer the data. Once it's all done, the DMA engine raises an interrupt and tells the CPU that it's all done. So as you can see, the CPU was only involved in the first step where we run the device driver to set up the DMA. The transfer happened through the DMA engine, and while this was happening, the CPU was able to do something else, right? We were not wasting CPU cycles. This is an example of a network stack in kernel, in Linux kernel. So what are we looking at? So this is your physical link, let's say Ethernet. This is your NIC, the hardware, the network interface card. This one is basically your DMA-able memory region. So this is the memory region that we're allocating to DMAs for our NIC. Now this is a kernel packet buffer, all right? So this is specifically for packets. Kernel has allocated a buffer, let's say. And this is the memory space of our user application. Now, before you start receiving packets, when you set up your system, the kernel will set up the NIC. So the NIC has this RX ring. So this is where inside the card, it has some storage capacity. When the packet comes, it initially is stored inside the device. So the kernel sets up address of this DMA-able region. So initially, your NIC doesn't know where to copy the data. So operating system sets up this the entries for this, says the first packet you get, copy it here. The second packet you get, copy it here, or so on and so forth. So operating system provides this DMA-able memory region to the device. Now we start running. Let's say a packet arrives. We look at the ring. We say, okay, we're here at this ring. It has an address. So we start the DMA transfer to the DMAable region. Once it's done, an IRQ is happening. So this is an interrupt. So the device, the NIC, interrupts kernel. Now the kernel knows the data is here in the DMAable region. It copies it to its buffer. At some point, the user calls the system call socket receive to receive the packets. Now we go copy the data from the kernel buffers to the user application, and that's like a full cycle. Not a cycle, but a full sequence of events to get your data. Okay. Now, you might at this point wonder, okay, wait, you talked about all these system call stuff. I've never seen them. I never used any like trap instruction or syscall instruction in my code. What are you talking about? And you might be actually right. That's right. You probably haven't ever seen a system call instruction in your life. The reason is because we have layering in our systems. So this is the full picture, right? So your applications are running here using the OS libraries, and the OS library is the one who calls these system calls. And once we have these system calls, we have these device drivers who would then talk to the devices. So it's all levels of indirection, right? And layers and after layers of abstractions that we have in our system. So your application usually just calls into system libraries like libc, for example, and then libc is the one who then goes and calls system call instructions. Okay, now let's look at an example. Let's look at a web server example. So I have the client here sending requests to the web server. And let's assume that this is kind of like a file server. So the client is asking for specific files. And once we receive it, we look at our files to see if we have that file. If we do, we read it and we send the content to the client. So we retrieve the request and reply to the client by that. Let's look at what is going on in this web server. So in the web server, there is a hardware, obviously, that is basically your machine, and you're probably running a kernel, running an operating system. And on top of that, you have your web server application running. So initially, your web server starts reading from a socket. So this is a system call. And at this point, your web server gets blocked if it is a blocking call. So you're going to wait for incoming messages. By doing this socket read, operating system allocates a buffer for you, right? And when a packet comes, we just saw what happens. After the request is come, we do the DMA, and once the DMA is done, we raise an interrupt. At this point, the device driver copies the data to the buffer. So at the end of this, we have the data in the buffer. So we can return to the user. Now we have the data. So we copy the data into user space and user memory, and we return from this system call. Now, inside your server, now that you have the request, you can process that request. So you probably look at your files. You want to see if you have that file, or you want to read that file. Let's say you know that you have it, you want to read it. So you call another system call. You say, read this file for me. Now, again, the top portion of your, the top half of your device driver sets up the SSD, your disk interface, whatever that is. The DMA happens, you get interrupted, You return from that system call and you give the data to the user. Now the user has the data. Now the user wants to send that data to the client. So how does that happen? Well, you call another system call. You call into a network socket write. So you write your data. This is another system call. And eventually that data is DMA to the NIC. And from the NIC, a packet is sent to the network. Okay, so in summary, we talked about 4 main concepts in operating systems. We talked about threads, address spaces, processes, and finally we talked about dual mode operation. With that, we're finally done with the second portion of the course, which was the operating system concepts. Okay, let's move on to part 3, which is synchronization. Now, a little bit of background on this. So for a few lectures now, first of all, there won't be a tutorial here. So I will have to remove this tutorial. So we don't have a tutorial tomorrow because I don't think I will be able to give that tutorial. Probably I'll move it to here, the tutorial on Wednesday, next Wednesday. But anyhow, so we're gonna actually, did it download? We're gonna, what? Weird. Mm-hmm. Let's download it again, maybe. Okay, so I will have to do it. On my computer. Okay. Oh, there is something with actually this PowerPoint. So weird. Okay, now that it has been repaired, I'm wondering if I can just push it. Courses, see public. What is? Oh. Sorry for this. Give me a second. What is happening? Okay, let's try again. Here, next. Nope, it's still bogus. Okay, so anyhow. Okay, so you can see my screen at least. We're good with that. So I have to see what's going on. Error might occur if the file is not completely downloaded. Feels like it was downloaded, but anyhow, let's go with my computer. So sorry for that. So okay, the background. We're gonna actually take few lectures to talk about concurrency and multi-threading. And we're not going to be talking about operating systems in particular. So it's going to be in the application level. So the reason we're doing this is because you guys probably have never had any exposure to multi-threading. In ECE, students take 252, which basically is on concurrency. So they already have seen and worked with p-threads, and they know synchronization, they know deadlocks and all of that. But you guys haven't, so this is your first time for most of you, not all of you, obviously. So anyhow, so I'm gonna spend some time, some few lectures, talking about concurrency and multi-threading. And this should give you a good idea of threads and multi-threaded programs. And once that's done, then we go back to operating system and talk about how to implement threads. So we're taking a detour to talk about multi-threaded programs. So just to set up what we're doing here. So we're not going to be talking about operating systems for a few lectures. So with that, let's start talking about synchronization and deadlocks. So we're going to first start by seeing what problems arise when we have a multi-threaded application. And then we talk about how we can fix it. And then again, once we're done with this, then we'll go back to operating systems and talk about how we can implement all of this. Okay, so you have to soon realize that there is in a multi-threaded environment, in a system with multiple threads, the reality might be different from what the programmer has in mind. So when you are coding, you have something like this: x equals x plus 1, then y equals y plus x, and so on and so forth. And when you're coding, so your assumption is the first line executes, then you go to the second line, and then you go to the third line. Now, in reality, that might actually happen, right? But it could also be that you execute your first instruction, your first line, and then you get suspended for some reason. Maybe an interrupt happens, maybe a timer goes off, or a packet is delivered, and then you context switch to some other threads, and then eventually you come back. And that could actually happen after your second line, or it could happen after third line. So you don't really know when your code is going to be interrupted. Now, this should not matter to you when your code is going to be interrupted. You don't care, right? But if you, so let's wait on that, but let's make one big assumption. So when you're executing these instructions, I just said, you might be executing your first line and then you might get interrupted. You might ask me, can I get interrupted in the middle of my first line? Like I have this x equals x plus 1. Can I get interrupted in the middle of it? And the answer is you could actually get interrupted in the middle of it. So the instructions that happen atomically, meaning that you cannot get interrupted in the middle of them, are few. For example, if you're doing a load or a store on a single byte, like just a word, like one single byte, if you're loading it or storing it, it's usually in most architectures, it's considered to be a atomic operation. So you cannot get interrupted in the middle of it. But if you are, for example, doing a floating point operation, loading or storing to a floating point, this instruction from your point of view is just one instruction. But when the hardware executes it, it has multiple parts because you're working with multiple bytes. And there is a possibility that you get interrupted in the middle of it. So it's not atomic. In x86, usually naturally aligned variables are atomic. What do I mean by naturally aligned? So naturally aligned means that the address of the variable is aligned to at least it's at least a multiple of the variable size. For example, if you have an integer in a 64-bit system, so it has 8 bytes. If the address of this integer is a multiple of 8, then in an x86 system, if you load or store to this integer, it's going to be atomic. So either the entire integer changes or none of it changes. So you can't get interrupted in the middle of it. Now, as I mentioned, there are a lot of instructions that are not atomic. For example, if you're doing double precision floating point operation, it's not generally atomic. Now, unless stated otherwise, in the lectures that I'm going to show you, I'm going to assume that memory operations like load and store are going to be atomic. So this is an assumption that we're going to make and go with it. I got a question. So is loading, storing a word? So a word is not 32 bits. A word is 8 bits. So it's 1 byte. So you don't have a word that is 32-bit. So a byte is just a word is only 8 bytes, and that's a word, right? So sorry if I made it unclear. So okay, yeah. So here, this word is basically a single byte. That's the definition of a single byte, is called word in computer architecture context. Okay. Ignore those two. There are some errors with my animation. So there are possible interleaving of threads in a multi-threaded application. So you might, let's say you have your system is running 3 threads. They might run like this. So thread 1 runs and then finishes. We go to thread 2. Thread 2 runs, finishes. We go to thread 3. Thread 3 runs and finishes, and that's it. So that's one kind of interleaving. It could be that you have a multi-processor, right? And all 3 threads run at the same time. So each one of them runs on a separate core. So all 3 of them are simultaneously running. And it could be that this happens. So you run a little bit of thread 1, you context switch to thread 2, you run a little bit of it, context switch to thread 3, and so on and so forth. Now, all of these are possible. You might say, can this cause any problem? Should I care about this? Do I even mind if there are different interleavings between my threads? And the answer is, it depends. It really depends. In some cases, if you don't program correctly, then yes, absolutely. This different interleavings could cause you trouble. And that's precisely what we're going to actually focus in the remaining lectures. from today for a while, at least for 2 or 3 lectures. Okay, let's move on. Let's look at an example. It's an ATM example. So let's say that we are writing this server for a bank, this server process, and there are different ATMs all over the country sending us requests, sending requests to this server for transfers, right? So this server just receives these requests, and they have some operation, right? For example, deposit or withdraw from this account this amount. Very simple, right? And once we receive it, we process it. Very simple. And here is the code for processing a request. So we say, okay, if the operation is deposit, then I deposit to this account this amount. If it is some other operations, then I do those operations. And let's say if you want to do deposit, then we say, okay, what is the account? Let's read that account. This might go to I/O, right? You're reading from your database to load that account. And then you look at the balance of that account, and then you deposit that amount. And then you finally store that account back to your database. So this is very simple operation so far. And as you can see, everything here is sequential, right? So we're processing one request at a time. Now, is this fast enough for a bank with millions of ATMs all over the country? Or maybe hundreds of thousands of ATMs? And the answer is absolutely not. You don't really want to sequentially go through all the requests, because you might get thousands or hundreds of thousands of requests per second. And you don't want to wait for I/O and stuff for each one of them, right? So what do? Well, maybe we should speed this up using multi-threading methods that we saw in the previous one, right? Maybe we should use threads. Okay, how do we do that? So I guess I don't have the code, but so if you remember, I think I had this example previously with creating connections. So instead of sequentially receiving and then processing, instead of here calling process request, we create a thread to process this request, and we move on. Now that thread is going to process this request for us, right? So instead of like this while loop calling a function, instead we call thread create, and then we pass this process request as the function that this thread should run. And that thread will be spawned, and it will go and take care of that request for us. Now, we're going to use this. Let's assume that we're going to use one thread per request. Now, this is definitely fast. It's definitely faster than sequentially doing requests, because now if we have a multi-processor system, or maybe if we have a bunch of servers, we can now run thousands or hundreds of thousands of threads at the same time. All of them are doing operations on the database. But does this, like, it makes it faster, but does it make it easier? Is there a problem? Could there be a problem with this? Here's an example. Let's say you have a spawn two threads, thread 1 and thread 2, and you have two requests. One of them, let's say, is a deposit. Both of them, let's say, are deposit. So in one of them, you're depositing $20. In the other one, you're depositing $30. Both of them to the same account. And let's say those two threads are running on your CPU. So there is one CPU running those two threads. So these are two different separate requests. And let's say in the first one, we load the balance for the account. And before we start doing the rest of it, which is adding, so it's a deposit, we wanted to add this amount to the balance and then store it, we get interrupted. So, and then we context switch to thread 2. Now thread 2 runs the same thing. This is also a deposit. So it reads again the balance. Now this is the $20, right? So we add the $20 and we store this. So now we have added $20 to this account. Now we come back to this one. Now, when we come back, we're going to restore the state of this thread when we left. And what did we have in this R1? R1 was the initial balance of this guy without this $20 extra, right? So that was in R1. Then we went here and added $20 to this balance. But when we come back, this R1 has the original amount. Now we add $10 to it, and then we save. So what happens? So we wanted to add $30 in total. So $10 here, $20 here. But with this context switch, $20 disappeared. So we added this $20, but then we changed it back. And we kind of nullified what this thread does or had done. So that's the problem, right? So this shows you when you have two threads, both of them working with the same data, we're going to have a problem if we are not careful about these interleavings. Now, if it was the case that thread 1 runs to completion and then we go to thread 2, this problem wouldn't have happened, right? So thread 1 would have loaded the balance. It would have added amount 1, and it stores it. Then thread 2 runs, reads, adds, and stores, and everything is fine. So one interleaving, everything is fine. Another interleaving, we have a problem. So the problem that we're facing is at very low level. So we have these two threads that are working on the same data. Now, if you remember in that a slide that I was asking you, should we care about these interleavings? The answer was it depends. What does it depend on? So here I have two threads. One of them is working with variable X. One of them is working with variable Y. Now, it doesn't really matter if I schedule these anywhere I want. So I can run thread 1, interrupt, go to thread 2. I can have any interleavings I want to, and the result will be the same because they're working on separate data. So the interleaving of the two thread instructions does not matter. So the result of them would be the same. The problem happens if you introduce a shared variable. In this example, so there is X, there is Y, but then thread B only works with Y, but thread A works with X and Y. Now, I have a situation where two threads are using the shared data. Now, do you want to guess what could happen in different interleavings? So what could be the X at the end of thread A? What are the possible X's that I could have? So let's say that we start with Y equals 12. What could be the result of this X equals Y plus 1? Now let's look at a bunch of examples. So this is one interleaving that thread A first runs, and then thread B runs. So under this one, so thread 1 runs X equals 1, and then X equals Y plus 1. So X eventually becomes 13. So the result of this run is 13. Let's look at another run, another interleaving. Let's say this happens. Let's say first thread B runs. So thread B is going to change Y to 2, then multiply 2 by 2. So Y becomes 4. Now thread A runs. Now we are having Y equals 4. So X becomes 5, obviously. And finally, let's look at another interleaving. So we just execute one instruction from thread B, context switch to thread A, and go back to thread B. And this time, the result is x equals 3. So 3 different results depending on how we run these 2 threads. This is called race condition. So race condition is a situation where the result of your program depends on the order and timing of the threads, as we saw. So in that case, we had a race condition. And it often happens when both of threads share some data with each other. So often, the reason for having a race condition is shared data between threads. Let's look at an example. This becomes a running example for the rest of the lecture. We're going to call it a too much milk example. So let's say there are 2 roommates, roommate 1, roommate 2, roommate A, roommate B. At 12:30, roommate A comes home, looks at the fridge. We're out of milk. So then it leaves, the roommate A leaves for a store. At 12:40, roommate A has arrived at the store, but roommate B comes home, checks for milk. There is no milk, and he also leaves for a store. At this time, A has bought milk and is coming home. So 12:50, roommate A comes home, puts the milk in the refrigerator. Roommate B has just arrived at the store. Roommate B buys milk and comes back, and oh no, we are having too much milk. So this is basically what we saw in a very milky example. Now for this example, let's say we want 2 things. First of all, we don't want 2 roommates to buy milk. So we want at most 1 roommate to buy milk. The second condition that we want to have is that we want somebody to eventually go and buy milk, because if you don't want too much milk, you can just say, okay, you come home, you see that there's no milk, and you don't do anything. You just sit home. So in that situation, you won't have too much milk, but then nobody would buy milk. So there would be no milk. And by the way, this problem would not exist if instead of milk there was ice cream. So if you have ice cream, too much ice cream is good. So it's just for milk. So I have 2 questions. When do race conditions happen? Where data is not shared between threads? We can talk about that, right? So just hold on to that question. If you don't get answer to that question, we'll come back to it. When do race conditions happen where data is not shared between threads? Okay, yeah. So for those 2 questions, just wait. Okay, so let's see. How can we solve this problem? So this is solution 1. Maybe we should leave note. If we are leaving for a store, let's put a note on the refrigerator that I'm leaving for a store. So how does it work? Well, I check for milk. If there's no milk, I leave a note. So first I check for milk, then I check for the note. Let's say I see that there is no milk and there is no note. So I'm going to go and buy milk. So before I go, I leave a note. I go buy milk, and then I come back. I remove my note, and that's it. So would this work? If you execute this by multiple threads? Let's look at some interleavings. Here is one interleaving. So thread 1 looks at milk. There is no milk. Now, before it continues, we context switch to thread 2. Thread 2 also checks for milk and sees that there is no note. So both of those 2 go. But before we continue, let's say we context switch. So now we context switch to thread 1 back. It now checks for note. There is no note. So it leaves a note. It goes buys the milk. and then comes back, removes its notes. Now we context switch back to thread 2. Where do we start? So thread 2 has already checked there was no milk, has already checked there was no note. So thread 2 is going to also go and leave note, buy milk, come back and remove note. So what happened was that we ended up buying 2 milk. So this solution kind of doesn't work. Now, it could work depending on interleavings. So under some interleavings, for example, if before we context switch to thread 1, we had left note, and then context switch to thread 1, then thread 1 would have checked for the note, and there would have been a note, and then we would have just 1 milk, so it would have worked. But under some other executions, like the one that is in front of you, it's not obviously working. So it occasionally works, sometimes it doesn't. Now, this is actually the worst kind of solution, because if you have a solution that sometimes works, sometimes it doesn't work, it makes your life super, super hard, because these are intermittent faults, and catching them is super hard. And I'm talking based on experience. So you run your code 100 times, it works, and then 1 time it fails. And then you kill yourself to reproduce that fault, and it just doesn't happen. And then after a while, it comes back. And it's just a nightmare to debug such code when you have intermittent faults. And I think they have a name. If I'm not mistaken, I think it's called the Heisenberg fault. It has nothing to do with what is it, Breaking Bad. Okay, moving on. Let's look at a solution 1.5. So maybe this note, we left it too late. Like we initially looked at the milk and then looked at another person's note, and then we left note. Maybe that's too late. Maybe let's put note at the beginning. So the moment we go to the refrigerator, pop, we push the note on the refrigerator, and then we do the checking. So here's the new code: leave note, then check for milk, and check for the other person's note. And if there are none, then go and buy milk, and then remove your own note. Would this work? So what happens with this one? Now, this might have worked with human beings, but unfortunately, it does not work when threads are in charge of buying milk. Let's look at one possible thing that could happen. So one possible thing that could happen is that nobody buys milk. No. So yeah, it could well be that nobody buys milk, right? Let's say you leave your note. The other person comes and leaves their note. Then we context switch to you. You check for milk, you check for notes. Now there is a note. And before you continue, let's say, so you're not going to do this, but before you remove your note, let's say we context switch back to thread 2. Now thread 2 checks for milk, there is no milk. Then thread 2 checks for your note, and there is a note, and nothing happens, right? Although if there is, so okay, there is one version of this that is too dumb, and if there is only one note, so you're leaving a note and then you're checking here, so you would never ever buy note. So maybe we should, okay, so I think I went ahead of myself. So I think this one was the dumb one, where you leave a note and then you check your own note, and this definitely doesn't happen because you left note and then you're checking your own note. Obviously, you're not going to go buy milk. Let's look at another one where we have 2 notes for separate people. So this one is the one that I started talking. So sorry, that's solution 2. So solution 1 was just dumb, right? You leave note and then you check your own note, and you're not going to go and buy. But look at this one. In this one, let's say different people leave different notes. So thread 1 leaves its own note, so note A, and thread B leaves note B. And then they check for each other's note. So thread A checks for thread B's note, and thread B checks for thread A's note. And I kind of spoiled it already. This is not going to work as well, right? So it's kind of like I sort of alluded to the interleaving that could cause this problem. And that is, you execute the first one in thread A. I think I actually have a slide. Do I? No. OK, so you leave note A. Before you check for note B, you context switch to thread B. Thread B leaves note and checks for your note. It's there. So it's not going to go and buy milk. But before it removes its note, let's say we context switch back to you. Now you're going to check for thread B's note, and it's unfortunately there. So you're not going to buy. So you exit. We go to B. B also exits. And now we don't have milk. So both of them in this interleaving checked for each other's note, and it was there. So both of them ended up not buying milk, right? OK, so this is kind of called a starvation, right? So we don't end up making progress on what we wanted. And if you remember, we had two properties that we wanted. The first one was we don't want two to go and buy milk, but we also wanted that at least one of them goes and buys milk. And this solution is not providing that. OK, so let's look at solution 3. Now, in solution 3, I'm changing the code a little bit. So instead of just checking for note B, I keep checking for note B, right? So this one, so in the previous one, right, I would check note B, and if it wasn't there, then I'm like, OK, I'm not going to go and buy. This one, I change it to while. So I haven't changed thread B's code, leaves note B, checks for note A. If there is no milk, it goes and buys milk. And if there is milk, then it removes its note. In thread A, I have a while loop. So as long as there is a note on B, I'm going to wait. Now, what does this give me? So this gives me this property that from thread A's point of view, if it finds out that there is a note from thread B, there are two conditions. Either thread B goes and buys milk and then removes its note, and then I can check if there is milk, and I will see that there's milk and I abort. Or thread B sees my note and doesn't buy milk and removes her note, and then I check, OK, there is no milk, and then I go and buy. So this kind of, here at X, thread A is going to make sure that thread B is done before it continues. So if thread B has started, then A is going to wait for thread B to finish and then check and see what it has to do. So does this work? Yes, it does work. You can see that it actually guarantees both of the properties that we wanted. So I actually have a proof, sort of a mathematical, not mathematical, but some notion of, analyzing the code. I'm actually going to jump from it. So you can actually, go over the slides and convince yourself that this actually works. And somebody's asking about deadlock. No, deadlock doesn't happen in this case. So again, you can look at this. I'm going to just jump over it. So there are some cases. So it basically comes to analyzing this X and Y. Again, I'm going to just skip over that. It's not that important, the proof that the code works. Now, let's discuss this solution. So this was our third solution. Let's see how good it was. Now, actually, before discussing, let's come and build up some definitions that we're going to use in our discussion. So first of all, we're now entering this this phase that we can talk about this shared state and talk about a piece of code that has to be executed only by one person, only by one thread. So that piece of code that we want it to be executed at any single time, but only a single thread, we call that piece of code the critical section, and we call that condition that we want only one thread to access it mutual exclusion. So mutual exclusion means that at any given time, I only want one thread to have access to that piece of code. And that piece of code, we call it critical section. So these two are two sides of the same definition. So critical section and mutual exclusion. In the example of too much milk, the critical section is this one, right? This, if we don't have milk, go and buy milk. So we only want one single thread at any given time to be able to execute these two lines, right? We don't want them both to buy. We don't want them both to look at this, whether or not we have milk or not. You could think of it as if x equals 0, then x equals 1, right? This milk is that shared variable that we care about. So every time anybody wants to read or write this, we want only one thread to be able to do that. So this becomes our critical section, and we want mutual exclusion on this critical section. We want only one thread to be able to execute them. And you can convince yourself, like going back, that this code in front of your eyes does this. So it only allows either B to do this or A. As I said, A will wait here for B to finish. If A detects that B has already started, then it will wait for it to finish before it accesses the critical section. And B the same. So B also checks for A. If A has started, then B just doesn't execute this code and it gets out. Now, with that introduction, let's talk about our solution. Now, this solution works, solution 3, but unfortunately, it's absolutely not satisfactory. It's unsatisfactory indeed. So first of all, the problem with it is that it only provides one critical section. What if I wanted to check a bunch of stuff, right? Then I would have to push all of them in one single critical section, right? I couldn't have a bunch of critical sections in different parts of my code. This becomes clear when we talk about other methods of ensuring critical sections. In those cases, it's much easier to have a couple of critical sections. The second one is it's too complex, right? For such a simple problem that we have, just check a variable and set it, it's too complex, and you have to convince yourself that it works, and you might convince yourself it works, and then you become doubtful, and so on and so on. It's complex. Analyzing it is complex. The third shortcoming is that if you go back to those two, you will see that they have different codes. So thread A's code differs from thread B's code. So we're just coding differently. What happens if I have 5 threads or 10 threads? What am I going to do? Like, how am I going to modify this method to deal with that? So first of all, I have to say there are modifications, and it's called Patterson's algorithm. So if you have more than 2, even for the 2 case, the one that you saw is a modified version of Patterson's algorithm. So if you just search Patterson's algorithm, you will see it slightly different than what we saw, but similar concepts. And you can actually extend it to multiple threads. It's fine, but it's just the fact that these threads have different codes is annoying. The last, shortcoming is that thread A kind of busy waits So that while loop that we talked about, or that you saw in thread A's code, it says as long as there is note B, just, you know, do nothing. But then that do nothing is a while true, so it's consuming CPU cycles. And let's say if you have one single processor, then A is gonna just run and not allow B to go and do its work. So it's gonna just run, check. Well, when B is not running, so it's not able to go and remove its note. And you're just gonna just consume cycles until eventually, let's say timer interrupts goes off and we context switch to B, and then B is able to go and remove its note. So it's kind of wasteful that we're doing busy waiting. And finally, unfortunately, I don't have time to talk about the third one, so we'll have to talk about it on Thursday. In fact, in new systems, this code actually doesn't work. And the reason is, for it to work, we need all the instructions to happen in a sequence that was specified in the program. Meaning that if I go back, I want the first line to happen first. Then I go to second line, third line, fourth. Like I don't, if I change the order of these instructions, it doesn't work. Now you might say, wait a minute, of course it's gonna just work in the same order of my program. And my response would be, sorry to shatter your dreams, but it's not the case. The hardware or the compiler could reorder your instructions without you knowing. So your compiler could come in and say, I think I can make your program faster if I change these two instructions. And from the compiler's point of view, it looks at your code and says, oh, they're independent. But the compiler doesn't know that there is another piece of code that is running that has dependency. So then that messes up everything. And even if your compiler doesn't, then there is a chance that the hardware does. So the hardware is going to say, I think I can run your code faster if I reorder your instructions, not knowing what those instructions are, and that could cause problems. So I will talk about the reordering in a little bit more, not much, but the bottom line is this works in ideal situations where your hardware and compiler is not going to reorder your instructions. The moment instructions are allowed to be reordered by the compiler or the hardware, then this doesn't work and it will be broken. So you will end up allowing two threads intercritical section. Okay, with that, I'm going to end. I got a question. Does the course go back to in-person lecture on February 7th? The answer is, I hope not. So personally, I prefer to continue online lectures. And I'm pretty sure if we poll students, if we poll students, they feel the same. But I have submitted a request to the chair, has gone to the dean's office, and has gone to the provost's office. So I'm waiting for that. So I have some personal health conditions that, anyhow, so I don't want to talk about it, but I have requested that we stay online. I should hear back from them. So whatever they say. So they're forcing everybody to go in person, even though seems like students, I mean, in ECE 350, students have petitioned to stay online. In different courses, they have said actually that they prefer to stay online, but we will see. So I have submitted a request that we stay online, but we will see. So I don't have an answer right now. As of now, we're going to go in person, but if I hear back, we might continue online. Okay, thank you for sticking around until again, 5 minutes late into the after the end of the lecture. Thank you to those of you who are watching these lectures online, and talk to you on Thursday. And again, we don't have any tutorial tomorrow. Take care, be safe. Talk to you later. Bye-bye.